Welcome back, everyone. On behalf of Forge College, I am absolutely thrilled to welcome you to today's explainer. We are diving deep into the foundational building blocks of the Web3 world, and today we're focusing squarely on Ethereum. Specifically, we are unpacking account identifiers and addresses, a crucial part of our Ethereum fundamentals track. Because let's be honest for a second, staring at a massive 40-character string of random letters and numbers for the very first time, it's mildly terrifying. But don't worry. We're going to break down exactly how these addresses are formed, what they actually represent, and why truly understanding them is absolutely crucial before you can do anything meaningful on-chain.
Now, I know what some of you are probably thinking. Wait a second, didn't we literally just finish installing and verifying the Solana CLI in the previous lesson? Well, yes you did, and seriously, huge congratulations on crushing that setup. But as any great Web3 developer will tell you, true mastery means understanding the blueprints of multiple ecosystems. So we're smoothly pivoting from Solana's architecture right back into the core mechanics of Ethereum. You've got to have this fundamental knowledge locked in before we can even start talking about things like balances, nonces, or smart contract execution.
Okay, here's our roadmap for this explainer. First, we'll look at the digital mailbox analogy. Second, deriving your address. Third, formats and EIP55 checksums. Fourth, the zero collision guarantee. And finally, next stop, on-chain state.
Let's jump right into Section 1, the digital mailbox analogy, separating identity from control.
We need to clear up a massive misconception right off the bat. I want you to think of your private key as the literal, physical brass key sitting on your keychain. That key is the one and only thing that lets you unlock and control your assets. Your Ethereum address, on the other hand, that is just a public mailbox number carved into a stone pillar on the street. Anyone walking by can drop a letter, a token, or a Bored Ape into that mailbox. The protocol, which acts as our digital mail carrier, routes those funds there without ever needing to know who actually holds the physical key.
So, the golden rule of Web3 really boils down to this. Addresses route messages and value. Control is entirely separate. Just because you have a mailbox number doesn't mean you can open the mailbox. Once you keep this separation crystal clear in your head, your account security will suddenly make perfect sense.
Moving on to Section 2, deriving your address. We like to call this the cryptographic assembly line.
So how do we actually get that mailbox number? It's a deterministic one-way transformation. Let's look under the hood. Step 1, we start with the 32-byte private key. In Step 2, we apply something called Sec 2.56K1 elliptic curve point multiplication. I know, it sounds like heavy math, but basically, it yields Step 3, a 65-byte uncompressed public key. In Step 4, we drop the formatting prefix, leaving us with exactly 64 bytes. For Step 5, we run those bytes through a hashing algorithm to get a 32-byte digest. And finally, Step 6, we literally just chop off the beginning and keep only the last 20 bytes. Boom! That right there is your raw Ethereum address.
Now, the absolute powerhouse behind that fifth step is Keccak 256. This is the specific cryptographic hashing algorithm Ethereum uses to scramble the public key. And the real magic here is that it's a strict one-way street. Think of it like a blender. You can't unblend a smoothie. It's mathematically impossible to reverse engineer an address back into a private key, which keeps your control mechanism totally hidden from the public.
A quick side note here for our aspiring smart contract developers. Contract addresses are actually derived using slightly different rules. They use things like the creator's address and a nonce, or an opcode called create2. But hey, don't let that trip you up. Whether it's an externally owned account operated by a human or a smart contract operated by code, the final output is always exactly the same, a standard 20-byte identifier. On the street, all the mailboxes look completely identical.
Let's look at Section 3, formats and EIP55 checksums, or as we call it, the paint job. How we represent these addresses really varies depending on who or what is reading them. Down at the protocol level, machines just use pure 20-byte raw bytes. Low-level developer tools will spit out hex, which is usually 40 characters starting with 0x. But let's face it, flat hex is an absolute nightmare for humans to read. So modern wallets use something called EIP55, which mixes uppercase and lowercase letters. And for ultimate readability, we map these to ENS names, like Vitalik.eth, which basically acts as a simple human phone book.
The pure genius of the EIP55 checksum is that it isn't just random capitalization. It is a built-in barcode. Basically, the system hashes the lowercase address and uses the resulting bits to dictate exactly which letters to capitalize. Why does this matter? Well, if you manually type an address and miss even a single character, that capitalization pattern completely shatters. Your wallet recognizes the error instantly and stops you from sending your hard-earned ETH straight into a digital black hole. It's a lifesaver.
Section 4. The Zero Collision Guarantee. Let's talk quality assurance.
160. That is the magic number that lets Web3 developers sleep at night. Remember, our address is 20 bytes long. Since there are 8 bits in a byte, 20 bytes gives us a mathematical space of exactly 160 bits. That means there are 2 to the power of 160 possible addresses out there. To put that into perspective, that number is so astronomically massive, it's roughly equivalent to the number of atoms in the known universe. So yeah, we are truncating data at the end of the assembly line, but the remaining space is so vast that accidental overlaps are statistically 0.
And we desperately rely on that 160-bit guarantee to avoid an address collision. An address collision is when 2 completely different private keys accidentally generate the exact same mailbox number. Imagine the absolute chaos if you opened your digital mailbox and found your neighbor's mail sitting there. Or worse, if they had the key to take yours. It would be catastrophic. But thanks to the sheer size of a 160-bit space, you can sleep soundly knowing this will practically never ever happen.
Finally, Section 5. Next stop, on-chain state, putting the address to work.
So let's bring it all together and review the core takeaways. Ethereum addresses are always 20-byte identifiers derived via checksum 256. Formats can range from raw hex to EIP55 and ENS. Mathematical collisions are theoretically possible, but practically impossible. And above all, always remember the mailbox model. An address routes value, it never proves control.
Which brings us to a provocative final question. Now that you know exactly how this 20-byte mailbox is constructed, how does the Ethereum protocol actually keep track of the balances, the transactions, and the data inside it? Well, that is exactly what we are going to explore in our next lesson on balance tracking and nonce behavior. Until then, on behalf of Forge College, thank you so much for joining me. Be sure to visit our website at forge.college to continue your Web3 learning journey and dive even deeper into this fascinating topic. Keep learning, keep building, and I will see you in the next one.